Okay, so um, welcome to the lecture number 3, which is a tutorial 1 of control theory 1. So the objective for this lecture is to show you how you can solve differential equation using two different methods. One is analytical method and another one is numerical method. And to illustrate uh, the accuracy of numerical method when you choose a proper sampling time. Okay. Why this one is not working? Oh, it's need me to sign in. Okay, I will go quickly because this part you have learned in the previous lecture already. Um, so let's see an example. You have a first order differential equation like this, and you consider only h from t positive, and with the initial condition this, then you can find the solution. uh, First, the solution, which is a combination of homogeneous solution and particular solution. So uh, once you have a solution like this, you can find the constant C and particular solution by substitute this equation to the initial condition. Okay, so in here you can find lambda equal to -2 and C is 5/2. So the final solution is this. So I don't go through the detail, you can read it later, and you have seen it already a couple of times already. um, so one interesting point is that for the system when t go to infinity, and you have h approach to constant, because when this exponent goes larger, e to the power to the minus infinity will go to 0. Then at the steady state you only have this part. Okay, it's called steady state. And here is the graph of this function. So it starts from 0, and when t go to infinity, the curve just approach to a constant, which is the particular solution. And another interesting part is that if you look, you want to check the behavior of the solution. Uh, if you have exponential like this, so you check whether it's stable, I mean it converge, or it's diverge. You can just look at the parameter a. Okay, so a is, if negative a is uh, minus a is negative, then the system is stable. Okay, if minus a is positive, then that solution diverge. It means unstable. So I try to use the term stable, unstable uh, together with converge and diverge from now. And the next part is numerical method concept for ODE. The first method I'm going to show is called Euler Method, which can be called first order approximation. This is the most simple but very, very useful, because you use it all the time uh, to for the controller to control your system, because you don't need to use sophisticated algorithm, you just need to use a first order approximation. Um, and first thing to do is to select sampling time, denoted by capital TS or delta T, and the sampling time must be small enough. And Euler approximation. So sometimes you hear Euler method, sometimes you hear Euler approximation, sometimes you can hear first order approximation. Okay, these terms are equivalent. So why we call it Euler approximation? First, look at here. Let's say the red curve here is the function h of t, and you pick at the time tk minus 1 here and tk here. Then the derivative, which is a tangent at the curve like here, can be approximated by this line. Okay, so uh, so the slope represented by the derivative h dot is the slope of this line, and delta h over delta t, here is delta h over delta t, this part is delta t, or the same as ts. So if ts is small enough, this line and this line are close together. So this is why it's called approximation. We approximate the tangent lines by this line that across at 2 points, and these 2 points are close together if you choose small sampling time ts. And so tk here, you can say it's k times ts, because if you sample like this continuously, consecutively like this, so at this part it's just k plus 1 times ts. This part this point is just k plus 2 times ts, right? Because this interval is just ts. Okay. Not just reduce the notation, not to have too many notation, just use k at time h at time kts by hk, and this one by hk minus 1, something like that. So then you substitute this into this equation, the original equation. You can have a discrete equation. So this is called discrete equation. So this discrete equation is obtained from approximation of this continuous equation. Okay, and if you solve the equation, I don't explain in detail. The goal is just you can formulate it as a geometric series, and then you can have the solution of the geometric series. Hk is equal to this. Okay, and then you make you compute it to have the curve. It looks just similar to the analytical solution. Okay, and interestingly, you can see that the curve starts from 0, same, and then it converges to a constant 5/2, just the same as the analytical solution. So this is numerical solution that you can compute at certain point. Okay, And what you can notice is that if uh, if R is um, yeah, if R is less than 1, I mean the absolute R is less than 1, then this series converge. Otherwise, it's diverge. Okay. And which k equal to yeah, actually this equation we have. Oh, this is only original equation, and this is the answer of the equation. So why do I have this one? Let me check a little bit. Yeah, this is the final answer is this one. The steady state converge. All right. Okay. The next part is to show you how you can compare uh, the solution and to visualize it. Uh, yeah, visualize by having the actual scale. So you can program. First, you choose sample time 0.4, and you take the time t from 0 until 4 seconds. Okay, and so here is the analytical solution, and this one is the the solution of the discrete system, which is the approximate from the original equation, right? So now you can see here the blue one is the analytical solution. Okay, analytical solution is the solution of the continuous system, continuous equation, and the numerical method to have the approximation. Then you get discrete equation and its solution. So the solution is um, yeah, the solution from numerical method represent the discrete system. Okay, so try uh, to be clear between continuous and discrete, analytical solution and numerical solution. And try to make this term clear, because when I use these terms, you can immediately catch up. Okay, now you can see the gap between these two curves, right? The gap, because the red one is just approximation of this blue one, and this is for 0.4 second of sample time that uh, I chose. What if I choose a smaller sample time? So t taken from 0.1 up to 4 seconds again, and then you can see that the gap between the two solutions is smaller, right? So what happened when I choose t even smaller than this, say 0.001 second or 1 millisecond? So of course these two curves will almost overlap, right? This means that uh, when you choose the small sampling, the sample time is small enough, you can represent it as the solution of the continuous system, right? And if you uh, choose larger sample time, then that one represent discrete system from the approximation. Okay. Yeah. So it means no matter complex system you have, equation you have, no matter how many dimensions of the system you have, as long as you choose small sample time and you make a simulation, that solution can represent continuous one. Okay? Because some system, there's no way to find analytical solution like this example, right? Especially for a nonlinear system. You have nonlinear system, yeah, most of the system, there's no way to find analytical solution. You can only use numerical method to simulate it. But how you represent it as a solution of the continuous system or represent the analytical system, it's just that you need to choose very, very small sample time. So this is the main point that you need to know from the lecture today. Yeah, the first thing. And then how can we use numerical method for higher dimension of linear system or nonlinear system? So actually for this system, it's very simple. You can solve it using analytical solution, analytical method to get this analytical solution, right? But it just the question is just that if you have a system which is more complex and you have system of equations, and the right hand side is nonlinear, what can you do? Okay, so here is just to show you that for this kind of system it's easy, you can solve it immediately using analytical method. But then if you have a system like this, okay, y1 y2 happen to appear on both equation on the right hand side. So, well, actually it's not very difficult for nonlinear system. There is a method to solve this kind of system. But what I want to say is that the higher dimension you have, the more complex, the more difficult it is to use analytical method to find the solution. So, yeah, actually, this question easy? Not really, right? Somehow you can find it if you know the method to solve it. But by the way, can we have a way to solve it even easier than some standard method to find analytical solution of a nonlinear system? Yes, again, Euler approximation. Even you have high dimension, 100, even 100 dimension, you can apply Euler approximation, and then you can program to solve such equation easily. Well, so very, very similar to the first example, you can have the form of equation is that yk equal to yk minus 1 plus this called the right hand side. Okay, right hand side of the equation, right hand side, yeah, just right hand side is just this part, right? So I can show it again. Why I call it right hand? Yeah, here it's called right hand side. Okay. So you can have a recursive formulation. So, and it can be easily computed using a computer program and easy to program. Okay? When you have a recursive form means a current value of a function depend on its previous value. Okay? So once you can compute this value, you can compute. I mean, once you can compute the function at this present time, then in the future, in the future one-time step, you can compute using this present value. So it's recursive like that continuously. Okay. Great. So this one is to illustrate that when you have a non-linear system, for this one, is it easy to find an analytical solution? No. Maybe you can never get. Maybe you can spend 10 years just to find the solution of this one using an analytical solution, and I'm still not sure that you can find it, right? But again, if you use a numerical method, where whatever the right hand side, you can compute it numerically, right? So the form of uh, discrete equation that you obtain from the approximation of this equation is just like this. To compute a present value, you just need previous value plus the previous value put into the right hand side function and time the sample time. And the smaller the sample time you choose, the better. I mean, the more accurate the solution you have. Okay, the next part, just want to introduce um, other numerical method is called Ringota. So you just learn Euler method, which is first order approximation, right? How you know that this first order? And Ringota method is fourth order. Yeah. So how can we uh, recognize first order or fourth order? So I will show you how to derive the Euler method in a different way. So first, uh, you already learned that the way we derive the first order approximation, just use Euler approximation, right? Uh, we say first order approximation, and this one also approximation. Okay, so I'm going to show you one method, I mean one way that you can derive for both first order and fourth order. Actually, it's from Taylor series. Okay, Taylor series. How you write it? Taylor's series. Uh, okay, if you have a function h, yeah, function h. Let me draw it for you here. H, let's say its solution must be some kind of curve, and you want to write Taylor series at this time. At this time is, yeah, if I sample it 1 ts, 2 ts, and up to this part, this point, it's k times ts, and this part is k, yeah, this point k plus 1 times ts, because this interval is ts. So here is h evaluated at the time kts, right? And here my drawing is not good, so good. Here is h evaluated at time k plus 1 times ts, right? So I will do the Taylor expansion around for the h here. So h at k times ts plus ts, because play k plus 1 times ts, but I just distribute, okay, ts times k and ts times 1 here, equal to, so I want to do the expansion with respect to this point hts, okay. So no, I mean at this, yeah, at this time, right? Yeah. So first I have h evaluated at kts plus 1 over 1 factorial derivative, first derivative of h with respect to time, and evaluate uh, time t equal to kts, okay. And here you can have kts plus ts and minus kts. Can you follow this? You can say this is like t1, and this one's like no, you can say this is like t2, and this one like t1, right? Okay, so this one like t1, and this one like t2 minus t1, okay. And then plus 1 over 2 factorial evaluate, yeah, evaluate at t equal to ts, okay, ts, and again this one, yeah. So the actually it's just same like this, and square, and then plus 1 over 3 factorial again. Now I don't need to write complete like this, just say it just ts power 3, and then plus 1 over 4 factorial yeah. Then but actually they are infinite term, right? Taylor series. Then you do approximation, which means you truncate some, you just take some uh, we call significant term, okay, and truncate other term. So for example, in Euler method, for Euler, you truncate only here. You only choose here. Yeah, you only choose here, and you ignore from the second term until the infinite term. And what is the logic that you can ignore the other term? It's because if you choose small sample time ts, because here is just ts and here is ts square. Okay, here ts square. Let's say if ts is 1 millisecond, then ts square become 1 microsecond, right? If you consider square of the unit, I mean 1 millisecond, if you square it, the value would be 1 microsecond square. So it's much smaller than ts, right? Ts square is much smaller than ts. And also actually the higher the term of the Taylor series, the denominator is higher as well. So it becomes small and small, so you can ignore a higher term. So from here, if you use Euler, this one, you can just say hk plus 1. And here you just say hk. And here you can say plus, this one is just h dot, but evaluate at t, you evaluate it at t equal to kts, okay? And times, here you times ts. And what is h dot? Our original equation of the differential equation is h dot equal to f of h and t, any f, right? So here you get hk plus, you can substitute f, and when you evaluate t as kts, you can write it just tk, and you evaluate h at the time kts, you can have just hk like this. Okay. Yeah, so this is first order, right? Because you take only the first time derivative. You take up to the first time derivative. And then for Ringota method, fourth order, actually the method take up to the fourth order here. But there is several manipulation to, I mean, many tricks to do the approximation. I mean, approximate, and approximate. Not just direct. Sometimes you cannot have the direct computation. You need to do some more approximation on these terms. But I'm not going to show that. You will just see. You will just use the method directly, that the method already built in most of software to compute for you. So you don't need to look into detail. You just be aware that Ringota is fourth order from truncation of the Taylor series. Okay. So up to this point, you have any question? Any question? Okay, if no, I show another point before I illustrate what I have explained by using MATLAB. So the next point here is to show you how to transform a second order system to be first order but with a system of equation. Because as you can see here, the method can apply to any dimension you have, but it must be expressed as a first order on the left hand side, right? First order. Okay. So what if you have equation like this? You have second order like this. So how can you apply the numerical method to solve it? Okay. Or you can have equation like this. Um, yeah. So with these two examples, I want you to ask yourself how can you implement the numerical method I just showed earlier for solving this equation. Okay. So any idea? Yeah, of course, first you need to transform equation into the form h1 dot equal to right hand side something, h2 dot equal to something. Here as well, or you can, yeah, you need uh, to transform it into, yeah, you need to change parameter, h1 equal to something, h2 dot equal to something. So how? Okay. Okay, for example one, actually you can use the same method. Let h1 equal to h and h2 equal to h dot. So the first equation would be h1 dot equal to h2, right? h1 dot equal h2, and then h2 dot equal to h2 dot would be h double dot. So you can get h double dot there from here. H double dot equal to what? Just move everything here to the right hand side. Then you can have minus omega n square h1 minus 2 zeta omega n h2 and plus ut. Okay. So here is the form, it has the form h dot equal to f of h and t, right? How about example 2? Yeah, again, let h1 equal to theta and h2 equal to theta dot. So you can have h1 dot equal to h2 and then h2 dot equal to, yeah, theta dot, yeah, theta double dot, and you move everything to the right hand side. You can have minus g over l sine h1. Okay, so again you have h dot equal to f of h and t, but just no t here, no problem. Then you can apply, if you want to use Euler method, you can just apply this one. Okay, yeah, actually just this one, right? And you use existing tool, you can use Ringota for. Okay, you have any question? So you already familiar with this? No, some of you not familiar with it, but some of you I think, yeah. So no question, you can have a break about 15 minutes.